silver, which exist naturally in the form of pure elements, were probably the first metals used by humans. As civilizations evolved, people discovered the processes needed to produce other metals. The discovery of these chemical changes literally changed the course of human history. By the end of this program, you will have learned to identify chemical changes known as oxidation-reduction reactions, or simply redox reactions. You will be able to analyze what happens to the electrons during redox reactions and identify oxidizing and reducing agents. You will discover that oxidation and reduction reactions always occur together, and that these reactions are very common in the world around us. The evolution of civilizations began when people discovered the transforming power of fire. Certain rocks and minerals, called ores, could be heated in a very hot fire to extract metals. The technology of metallurgy had arrived, moving humans from the Stone Age to the Bronze Age to the Iron Age. As people learned more about the science of chemistry and the technology of fire, a variety of metallic ores were transformed into increasingly useful metals. Although the process of refining varies from one metal to another, it typically involves a large volume of metallic ore that is reduced to a smaller volume of elemental metal. The term reduction came to be associated with producing metals from their compounds. But chemically, how is reduction achieved? As the technology of metallurgy evolved, scientists began to examine its chemistry. In the case of reduction, the development of new technologies led to scientific discoveries.
Reduction was first described as the loss of oxygen from a compound. In the reduction of iron ore to metallic iron, oxygen is removed from iron 3 oxide. This is done by heating the ore with carbon in a huge blast furnace. After a series of reactions, molten iron flows to the bottom of the furnace where it is collected. To obtain a metal from its ore, we need thermal energy. But we also need a substance to act as a reducing agent, causing the ore to lose oxygen. An effective reducing agent for iron ore is carbon monoxide. At high temperatures, this reducing agent causes iron ore to lose oxygen and become elemental iron. This process is called reduction, and the chemical that causes the reduction is called the reducing agent. Other ores can go through the reduction process. With the addition of thermal energy, tin 2 oxide can be reduced to tin metal using carbon as a reducing agent. Notice in each of these reduction reactions, the metal element is produced from the ore. Typically, a large volume of ore is reduced to a smaller volume of metal. By the 19th century, scientists realized that they could pass an electric current through a metal ion solution, and this would reduce the metal ion to a metal element. Scientists had proposed a model of the atom containing small negative particles called electrons. They related the electron to the reduction process.
I'm here with Carmen, who set up an experimental design to help us understand the role of electrons in reduction. So, Carmen, tell me what you've done so far.
Well, here I've set up a control, and here we have a power source. And as you can see, it's not connected. And then as you can also see, our carbon electrodes have no signs of plating of any kind on them.
All right, there's no change whatsoever.
That's right.
Good.
So then over here we have our experimental cell. And as you can see, it's definitely connected up to our power source. And if we take a look at our carbon electrodes, there's definite copper plating on the one electrode.
Okay, so I guess the question is, why the copper plating on that electrode? Well, it all has to do with reduction. Now, reduction is a process in which electrons are gained. And in this particular situation, every copper 2 ion is accepting 2 electrons, or gaining 2 electrons, and therefore is being reduced to an atom of solid copper.
Which is what we saw plated to the carbon electrode.
Exactly. Now, this was all done on a small scale, and we can see exactly the same process in a much larger scale in an industrial setting. Let's have a look.
This is our power source here for the electroplating end of it. It's a DC system. and we're running X number of volts and X number of amps type of thing. It varies with every load. The way our tank's constructed here is we've got a couple of anode bars, which are copper anodes, are on. There's anodes inside each one of these baskets, and they're little balls made out of pure copper. And then the part that we are plating is on the cathode bar, which is your negative polarity. The solution is essentially a copper sulfate solution with sulfuric acid, to give you some idea of color. And I've got a part here that's being electroplated right now. And you get a nice shiny copper finish.
Well, Carmen, I've got another question for you here. Why do the copper ions accept 2 electrons? Why not 3 or why not 4 electrons?
Well, if we look at our copper, we can see that it has a charge of 2+. And we are adding 2 electrons, which is the same as a -2, which equals 0.
So really, all you're doing is making sure that the charge is conserved.
That's right.
Okay. Now, can you handle another question?
Sure.
All right. Do we always need a source of electricity to cause the reduction to happen?
No, but we always need electrons.
Ah, okay. Can you show me what you mean by that?
Yes, actually, I have another experiment set up over here in which there is no source of electricity. And then I'll be placing a strip of zinc into a copper 2 sulfate solution.
Can you tell me exactly where these electrons would come from, though?
Well, let's see. If I go and write a half reaction for the zinc, you see that zinc, solid, goes to zinc with a 2+ charge, aqueous, so that's ions, plus 2 electrons. And it's these 2 electrons that are used up here with the copper ions to make the copper solid.
Okay, so zinc supplies the electrons that reduce the copper ions, right?
That's right.
Okay, well, I'll tell you what. Why don't we go over here and have a look and see what's happened to that zinc that's in that solution?
So here we have our zinc, and as you can see, there's definitely some copper forming
yeah,
at the bottom over here.
right, you can see it.
Quite well. And then if we are to take this out and to wipe it off, we can see that copper is not only produced, but that the electrode has been corroded.
Okay, well done. Thanks, Carmen. So we've seen that whether it's because of a power source or because of electrons supplied from some other chemical species, reduction all boils down to one thing. It's the gain of electrons.
Let's summarize our 2 definitions of reduction by using this chunk of iron ore and this cast iron frying pan. Applying our first definition, an empirical definition, reduction is a process in which there has been a loss of oxygen. Iron ore loses oxygen to become elemental iron. Applying our second definition, a theoretical definition, reduction is a process in which there has been a gain of electrons. In this example, reduction occurs when the metal ions in iron ore are converted to metal atoms by gaining electrons.
Long before humans discovered the technology of metal refining, they were using the technology of fire. By the 18th century, scientists recognized the role of oxygen in burning. The isolation of oxygen led to an understanding of burning or combustion as the gain of oxygen by a fuel, hence the term oxidation. In 1789, a French chemist named Antoine Lavoisier discovered that combustion involves the reaction of oxygen in air with carbon and hydrogen in the fuel. The term oxidation was used to describe reactions in which one of the reactants was elemental oxygen. All combustion reactions are examples of an oxidation process, like the burning candle or the combustion of gasoline. Gasoline, which is primarily octane, burns an oxygen and oxidizes to form oxides of carbon and hydrogen. Since oxygen caused this oxidation, it is called the oxidizing agent.
An Another example of the oxidation of fuels occurs in the body when the body converts food into energy. In cellular metabolism, the oxidation process converts foods such as
carbohydrates into carbon dioxide and liquid water.
That's right. And because the oxygen is causing this oxidation, it is called the oxidizing agent. Metals can also undergo oxidation, as Carmen and I will now demonstrate.
Well, we're going to burn a strip of magnesium in a combustion reaction.
That's right.
So we should put our goggles on.
And the reason for that is because when magnesium burns, large quantities of ultraviolet light are released, and so very harmful to the eyes.
And we should also put some gloves on because
That's
we're
right.
burning. Yes.
Okay. So this match will be our ignition source.
And we will pick up a strip of magnesium.
Good. Now, sometimes it takes a while for the magnesium to light, but it's well worth the wait. And there it goes.
There it goes. There we are. And
Okay.
we can remove our goggles. And
Well, what's the first thing we notice?
well, in comparison to this strip of magnesium, our original strip, we can see that it's a white powder has been produced.
That's right. Let's take a look at the reaction equation. The magnesium combines with oxygen to form the white powder, magnesium oxide. Because the oxygen has caused the magnesium to be oxidized, it is the oxidizing agent. Now, some oxidation processes can occur quickly, but others more slowly. For example, iron can combine with oxygen to form iron 3 oxide, a component of rust. This occurs at a very slow rate. Let's take a look at its reaction equation. Again, the iron is oxidized by the oxygen to produce the final product, and because the oxygen causes the oxidation of the iron, it is called the oxidizing agent.
Late in the 19th century, chemists made an important discovery about oxidation. They concluded that the reaction of oxygen with various substances was one special case in a much broader class of chemical reactions involving a loss of electrons. Oxidation came to be defined as a process in which electrons are lost. And speaking of a loss of electrons, Carmen, you recently performed another experiment. Perhaps you could tell us about it.
Well, let's see. In this experiment, I placed a piece of copper solid into 20 milliliters of a solution of concentrated nitric acid. And then as you can see, the concentrated nitric acid is colorless, and it changes to a blue color because the copper 2 ions are blue. And this occurs when the copper solid is oxidized into copper 2+ ions and electrons.
Okay, wonderful. Well, the process that Carmen was talking about can be summarized right here on the screen. Solid copper, which was placed into the originally colorless nitric acid solution, was dissolved and formed copper 2 ions. Now, these copper 2 ions are what gave the solution the blue color, which appeared later on. And of course, there were also 2 electrons released for every atom of copper which was oxidized into copper 2 ions. So the process is oxidation, and oxidation can be defined as the process in which electrons are lost.
Let's summarize our 2 definitions of oxidation using this shiny steel nail, which after all is mostly iron. Applying our first definition, the empirical definition, oxidation is a process in which there has been a gain of oxygen. Here, the iron metal reacted with oxygen in the atmosphere to produce iron 2 hydroxide. Applying our second definition, the theoretical definition, oxidation is a process in which there has been a loss of electrons. In this example, oxidation occurs when the atoms in elemental iron are converted to ions by losing electrons.
We can now compare the processes of oxidation and reduction. We can do this by reviewing the terms. Let's have a look. Reduction is the loss of oxygen. Oxidation is the gain of oxygen. Using our second definition, reduction is a gain of electrons. Oxidation is a loss of electrons. Now, to help you learn this and remember this, I have a little trick. Let's have a look. Gain of electrons is reduction. The letters of each of these terms are G-E-R. This spells GER. Now let's have a look at oxidation. Loss of electrons is oxidation. Letters representing the first part of each of these words, L-E-O or Leo. And what does Leo say? Leo says GER.
We live in an electrically neutral world. Whenever one substance loses electrons, another must gain them. That is, oxidation and reduction always occur together in what chemists call reduction-oxidation reactions, or redox reactions. No substance is ever oxidized unless something else is reduced. In other words, electrons are transferred from the substance being oxidized to the substance being reduced. For example, the reduction of iron ore in a blast furnace would not occur unless there was also oxidation taking place. As iron 3 oxide is reduced to iron by gaining electrons, carbon monoxide is oxidized to carbon dioxide by losing electrons. Combustion was another example we looked at. Combustion could not occur unless magnesium was oxidized and oxygen was reduced. Let's take a look at another experiment which shows the electron transfer system in a redox reaction. Carmen, you did something earlier. Could you tell us about it?
Well, in the experiment, I demonstrated a redox reaction between zinc and copper disulfate. And as you can see, I placed the zinc strip into the copper disulfate solution.
Right.
And observed for evidences of a reaction.
Okay. Well, this particular reaction can be described by this reaction equation here, a single replacement reaction. But the problem is, this doesn't tell us exactly what's happening in the redox process. So, Carmen, what can we do to simplify this equation?
Well, we can do this by writing an Ionic Equation, which is received first by writing a total Ionic Equation.
Okay.
And as you can see, we separated the copper 2+ ions from the sulfate ions. And you can also see the sulfate ions, nothing happens to them, as they're spectator ions, and they can therefore be crossed from the equation.
Okay, we can divide them out. Now, spectator ions are any ions that are present but not actually involved in the reaction. So what we wind up with is a net ionic equation, and that's what we have right here. So let's have a look at this and see if we can determine a little bit more about what's actually happening in this redox process. And let's start just with the copper 2 ions. Carmen, what can we do now?
Well, let's see. If we were to write a half reaction, we would see that the copper ions, 2+ ions, plus 2 electrons is reduced to copper solid.
Okay, so we've got a conservation of charge here. You can see 2 positives, 2 negatives. Net charge then is 0 on the reactant side. Net charge 0 on the product side. So this is the reduction process. But tell me something, Carmen. How do we know this actually happened?
Well, if you look back at the experiment, you can definitely see some copper solid produced at the bottom of the U-tube.
There is a whole lot of copper there. So there's definitely evidence for the reduction of copper. And remember, reduction is defined as the gain of electrons.
Or GER.
Right. Okay, now let's change gears and look at what happened to the zinc.
Well, if you were again to write the half reaction for the zinc, we would see that zinc solid is oxidized into zinc 2+ aqueous plus 2 electrons.
All right, and once again here, just like before, we have 2 positives, 2 negatives, 0 net charge on the product side, which matches the 0 charge on the left.
That's right.
All right, now just like I asked you for the copper, how do we know this happened?
Well, again, if we were to look at the U-tube, you'd notice that on the left side, the solution is colorless, while on the right, it's a definite blue. And this occurs when the blue copper ions are replaced with the colorless zinc ions.
Okay, now remember, the reason why this replacement, so to speak, occurred is because the copper 2 ions, which we originally had, have been reduced to solid copper, whereas the solid zinc has been oxidized to zinc 2 ions. So we have this oxidation happening. Remember, oxidation is defined as a loss of electrons.
Or LEO.
And if I may, so overall then, this is what's happening. The zinc is oxidized to produce electrons, and it is these electrons which are being accepted by our copper ions.
That's right.
Now, we have a name for the solid zinc. Zinc is called the reducing agent. And a reducing agent is defined as a substance in a redox reaction that donates electrons and is itself oxidized. Now, we're going to focus a little bit more on the role of reducing agents in redox reactions, and that's what we're going to have a look at next.
Now, we've just seen how a reducing agent is oxidized by losing 2 electrons. Now, these 2 electrons go to the copper ion, Therefore, we call the copper ion an oxidizing agent. The copper ion gains these 2 electrons to be reduced to metallic copper. Let's look at the definition. Oxidizing agent, a substance in a redox reaction that removes electrons and is in itself reduced. All right, so now let's see how a redox reaction and a Christmas tree fit together.
Here's another demonstration of a redox reaction I think you'll find really interesting. In these 2 beakers I have some copper trees. And in this one it's a framework of copper wire, and in this one an actual copper tree. And I'm going to add some silver sulfate to each beaker. Now we're going to watch and see and look for any physical changes that occur. But to help us out, I've pre-prepared some beakers before the segment, and take a look. And you can see that there's silver has been precipitated on both Christmas trees, with the exception of this strip down the middle of this second one that we coated beforehand so it wouldn't react. And you can also notice that the color of the solution is definitely blue. Well, let's take a look at some half reactions and see if we can explain what's happened. Here's the half reaction for the reduction of the silver ion. And the silver ion has gained an electron and become the silver atoms that you see precipitated on the tree. Remember that a gain of electrons is reduction, so this is a reduction half reaction, and that means that the silver ion has been reduced. Here's the half reaction for the copper. Now the copper has lost 2 electrons and become the copper 2+ ion. You remember that a loss of electrons is oxidation, so this is the oxidation half reaction, and therefore the copper has been oxidized. And it's the copper 2+ ion in this half reaction that accounts for the blue color. 2 silver ions collide with a copper atom, and the 2 electrons from the copper atom are transferred to the silver ions, changing the silver ions into silver atoms and the copper atom into copper ion. Now what that means is that copper is the reducing agent, and remember that the reducing agent gets oxidized. It also means that the silver ion is the oxidizing agent, and remember that the oxidizing agent gets reduced. I want to show you some more of this reaction, but we're going to do it a little bit differently. I've got a microscope set up here with a camera, so we can look on a microscopic level at this redox reaction that we've been talking about. Well, here's a little piece of copper wire, and I've taped it to a slide. And I'll put it onto the stage of the microscope. And let's take a look and see what we've got. Okay, there you can see the piece of copper wire. Now I'll just scroll along here to find the edge, and you'll see why in a minute. Okay, now what I'm going to do is I'm going to add a drop of silver sulfate. There. All right, you can see the crystals growing right now. There they are. And the redox reaction is occurring at quite a furious pace. And you can see those little things that look like trees. Well, that's silver crystals forming in the solution. Here, let's scroll over a little bit. Wow, it looks like a whole forest of little silver crystal trees. Excellent. And there's a shining example of a redox reaction.
The distinction between redox reactions and other types of reactions is an important one. Let's compare them. First of all, let's look at a double replacement reaction. Here we have ions forming ions without a transfer of electrons. In each case, we have the ions unchanged in every single species. Now, an example of a double replacement reaction would be an acid-base reaction. There's no transfer of electrons, therefore it is not a redox reaction. Now, let's look at a single replacement reaction. This is a redox reaction. In our first ion, sodium ion, it is unchanged. Therefore, there is no transfer of electrons. But in chlorine, the atoms in chlorine gain electrons to become chloride ion. This is a transfer of electrons. Next, bromide ions give up electrons to form the atoms in bromine molecule. Again, there is a transfer of electrons. This is a redox reaction. Now, besides single replacement reactions, other examples of redox reactions are combustion reactions, corrosion of metals, formation reactions. All of these are redox reactions because there is a transfer of electrons.
We're here with Jerry Bolton, Senior Manager from Sherritt International, an integrated nickel cobalt producer. Hi, Jerry.
Hi, Elaine.
I was just wondering, what's the industrial name for this reaction that we see in this process?
The name for the reaction is hydrogen reduction.
Okay. What is being reduced and what is being oxidized?
Either nickel or cobalt metal is being reduced from solution, and the chemical that is being oxidized is hydrogen. It's being oxidized to the hydronium ion or acid. The reaction is between nickel diamine sulfate and hydrogen, and the hydrogen is oxidized to acid, which is neutralized by the ammonia ions to make ammonium sulfate, and the nickel is reduced to elemental nickel.
Okay, what form is the nickel marketed after it's been produced?
The nickel is originally produced as a metal powder, pure metal powder, and that powder can be turned into metal strip, which is used for coinage materials, or it can be made into briquettes. But the majority of the nickel is used in the production of stainless steel.
Of what use is the byproduct of ammonium sulfate?
Ammonium sulfate is a fertilizer, 2100. The 21 means that it's 21% nitrogen. But it's also 24% sulfur, and that's important for prairie soils, some of which are sulfur deficient.
Why are autoclaves used in this process?
Autoclaves are used because the process must be contained. It's a high temperature and high pressure process using hydrogen gas, so a very secure containment is required. All industrial safety precautions are observed. Explosion-proof equipment is used throughout in this area. Operators are highly trained, and whenever maintenance is being conducted, the area is thoroughly checked to make sure there are no explosive gases.
Let's review redox reactions by summarizing the definitions of reduction and oxidation. Reduction is the gain of electrons, or, to help us remember, GER. Oxidation is the loss of electrons, to help us remember, LEO. Next, reduction could be called the loss of oxygen. Oxidation is the gain of oxygen. And last, reduction, the substance reduced is an oxidizing agent. Now in oxidation, the substance oxidized is a reducing agent. Many important chemical changes involve oxidation-reduction reactions. The corrosion of metals, most forms of energy production, and many life processes take place by the transfer of electrons.
Yeah, but I'm trying to focus the copper. And that's a shining example of a redox reaction if I ever saw one.
Okay, how about another question? All right, do we need electricity to cause the reduction of these copper ions to occur?
No, we do for these copper ions, but most ions don't need electricity. They just need electrons. You said it wrong.
Yeah.
Cool, look at that. Sorry, I wasn't here. Well, up to that point, it was pretty good. This was the easy part.
I know, no kidding.
Fun part too.
Yeah.